Okay. Also, how are you today?
Good.
Okay, perfect. I'm good. All right, so I'm gonna talk about the. I think you were in the last class. You remember this one too? But we talked about the cyclohexane. So we try to draw this in a chair conformation. So as you remember, this is what we kind of drawing over here. So let's try to draw one over here. So try to draw the chain conformation of the cyclohexane here. I think one trick you can do is try to make two lines parallel to each other, okay? And try to make some dot where you have a same on the other position here and here. And just try to connect those dots. Okay. Then you can have another one on the other side. Two parallel lines, and try to get the dots on these two. And it looks like this one. So whenever you do this one, only thing you have to do is try to find out the axial positions. So whenever you do this, the lines are heading up, this point up, and that's the one that lines goes down, down, and down. And this is where you can put some hydrogen on those positions we call axial position. So it just only, it's like a y-axis. It goes to go up and down like an axis. Okay? This is the axial position. And then we have some equatorial position we're gonna fill out. It's pretty simple too, but just require a bit of practice. So with those lines here, so it goes to this one right here, here, and these lines are here, here, and here, and these lines are here, and then these lines are here, like this. So this is the way we draw it. So we can do the same here. That's pointing up, axial position, and those three. And there's a three down axial position here. And then this is the parallel to this line, those two. And those, okay. And those, okay. This line, right? And this line, right there. That's it. Do you think it's kind of makes sense? Okay. So we'll get to this one really more with example. But this is a kind of good trick you can do when you try to draw the all the axial. Oh, and those ones that we call equatorial position. Meaning it's more like not up and down, but it's more like a left to the right. Either just slightly up, slightly down. We call this equatorial position. So this is how we can draw the chair conformation of the cyclohexane. Also, you can fill those with the hydrogen and those equatorial position and axial position on this two possible chair conformation caused by ring fluid. So this is something we might have to do a bit of a practice, but I'm pretty sure you will get used to it for sure sometime soon. But just remember these two things: axial position, equatorial position. This is something you have to remember for next subject. This is very important to know where this would be placed on each carbon and so forth. Okay. Kind of makes sense, right? Can I move on? So the thing is, we have a cyclohexane. let's try to put the one group over there. Okay, so try to put one method group. Okay. So it will just looks like this. Okay, it's like this one. Okay, and then I'll try to draw this one on here. Okay. So maybe I can try to do it on here. Okay. So if you don't see, but there's a hydrogen also there too, because the carbon should have 4 bondings. So the way you have a methyl group on the cyclohexane, you also have a hydrogen here. So maybe you can put this on this way. Okay. And then let's try to think that we can do the ring flip here. So once again, it's not about it's not like we're flipping this one 180 degrees. That's not what we mean by ring flip. We're just gonna switch this one and this one here. So let's try to do that too. Over here. So if you look at this one here very closely, this is obviously axial position. This is like an equator type of the direction over there. So this is the axial position. This is the equatorial position here, right? There's hydrogen is equatorial position, axial position here. And another thing you have to know is this is axial position heading up. Right? This is axial position, but it's heading up. And this is equatorial position, but it's actually slightly going down, right? So it's slightly down. Okay. So when you do the ring flip, you're moving these two in this way, right? This way, and this goes down and up, right? So this position is now here, right? And then when you put this one down, so now this is going down, right? And this is axial up, right? It will become equatorial position up. Because it was up. So it's always up. Once it's up on here, it has to be up in here, but just equatorial position now. Because now it's heading down. Okay? So this is going up. And now this hydrogen was the equatorial position down, and now is axial down. Okay, the kind of makes sense, right? Kind of, okay. So the let's try to do one more, and maybe we can move on. How about we have the methyl group over here, okay, and we have a hydrogen in here. Okay, so this is also equatorial position, but it's heading up, slightly up, and this is axial position, but it's heading down. Okay, so if you do the ring flip, this is position we have over here, right? Ring flip. So in this case, this is an equatorial position up, so they're going to be axial up. This is still up, it has to be always up. But now in axial position, it's axial up. And now this is axial down, so it will be equatorial position down. See the equatorial position is. So even though you do the ring flip, you can always look at where there is and which position and which direction. Make sense, right? Okay. All right. Okay, so there's there's one more thing I want to go over. That is, whenever you have you have this case, right? This one, like we did before. Okay, so you have this one over here, and you can put it down in this way. So this is two, what can I say, confirmation you can have from the wing flip. Once again. And then whenever you have a methyl cyclohexane, you're going to have this form, this conformation is more preferred. Because this is the more stable. The reason is this one. You see those ones and the exit position and equatorial position here, right? But I didn't draw here. They are the implied hydrogen. You can also see those hydrogen over here, right? I mean, I can draw all, but I'm not gonna do. So if you look at those ones here, here, okay. And they're going in exit position. They're going to have some type of static interference because if you think about this methyl group here, if I draw it more here, this is actually what it looks like, right? Okay. And then the adjacent hydrogen to those other axial position hydrogen on the methyl group will have a slightly discomforting for the spacing problem here. So we call this 1,3 diaxial interaction. So because of this one, they're going to have so each would take about 3.8 kilojoule per mole type of discomfort there, but there are two. So in total, they have about 7.6 kilojoule per mole type amount of the discomfort in energy unit. The experience, we call this 1,3 diaxial interaction. So obviously, when you put this in the methyl group on the equatorial position going on this side, obviously it'll be more stable because there'll be no spacing problem on nothing on this side. So whenever you have a methyl cyclohexane, there are the two types of conformation are possible from the wing flip, but mostly they prefer this form because of they try to avoid this 1,3 diaxial interaction caused by those hydrogen on exit position from other hydrogen in the methyl group and also on the exit position too.
What is the 1 and 3? Where did that come from?
What is
like in the name, 1, 1,
oh,
3. Where
yeah.
did that come from?
So this is so you see there's the hydrogen, right? This is also in the exit position, right? Mm-hmm. But there are two. So that's why we put the diaxial interaction. And there's 1, 3 because there's the one carbon away. So it's 1, 2, 3, 1, 2, 3.
Okay.
So that you can name it that way. But the main driving force anyway is static hindrance, static interference. But we, based on the position and the direction, we just try to name it more in a clear, specific way. That was very good advice. So this is amount of the discomfort they don't want to experience. So obviously, the compound always wants to be in a more as possible form they can do. So they'll prefer this form if there's a chance. Obviously, if we have enough energy to overcome this like this amount of energy, they don't mind to do it, but why would they? Even though we have a link flip for methyl cyclohexane wise, this would be more preferred for sure. Because makes sense, right? Okay. Alrighty. Okay, so let's move on. So we have maybe we can talk about the 1,2-dimethyl cyclohexane now. So in this case, we're gonna put the methyl group on 2 methyl groups on the cyclohexane like this. So let's try to put it on the chair conformation here. So there's one thing I want to tell you is you remember the ring structure is also cannot rotate, right? So the ring structure will have either, if there's a two, they can have either trans or cis. Okay. So the trans means those alkyl groups are on the same side. I'm sorry, on the other opposite side. The cis means it's on the same side. So the one we're gonna talk first is cis one, meaning you're gonna put the 2 methyl group on the same side. So you have to put like this. Okay. It doesn't matter if you put the dashed line, because as long as they're on the same side, it's the same compound anyway. Because you just flip it, that's the same. So this is here. So this is the cis 1,2-dimethyl cyclohexane here. And then you don't see it here, right? But we always imply the hydrogen, right? So you can always assume there's something like this one. Okay, just try to remember this one. So anyway, so if you try to put this in the here, what they can do is we're gonna put this one maybe here and here. It doesn't matter which one you choose. Maybe I can put this one here and this one in here. Okay, so this wedge once again is going toward to this direction, toward to where you're looking at. So the wedge means it's going up toward to you, but the dashed line is going the other side of this plane right here. So let's try to make those two up position then. As long as if you put it all these two up position or down position, doesn't matter. But just in case, we can put this in the same side, meaning just two up. So if you put those two in the same side, it has to be either only up position, either equatorial position or the axial position. As long as it's up, means it's a cis. Okay, so this is maybe here, and we can make this equatorial up because it's heading slightly up, right? So here, okay. And also this position have a equatorial position down, axial position up. So we're gonna put it in here. Okay. So those hydrogens are also on the same side on the back, down, down, up, right? Do you see? It's good, right? Up, and down, down, right? So let's do the ring flip over here, okay? Ring flip. If we do the ring flip over here, okay? If you do the ring flip over here, you're going to have this position goes to here. This position goes to here. Okay. So this up position will be coming up, right? And this is up, So it'll be up equatorial position. Okay. So in this case, you're going to have this one. If you look at this one here, this is let me try to. So do you see what type of interaction you can also possibly do with this one? Perfectly, perfect. You're gonna have 2, 1, 3, diaxial interaction, right? Perfect. Good. And that's about 7.6 over here. Okay. And then one thing I need to tell you is do you see this one? Okay, let's have we have 2. There's okay. And then there's another one you can see is if you look at this one, these 2 carbons front and back as a Newman projection, if you remember. Newman projection. This is what it looks like, right? Okay. So in this case, you have this carbon right here in the dot. Okay. This carbon on the back looks like this, and they heading up, right? And this position is equatorial up. Okay. Okay. So do you remember Gauss conformation? So there's a method group is even though it's a 60 degree apart, it's a stagger, right? It's a stagger. But if this is 2 bulky groups kind of close enough to be 60 degree only away, it's the Gauss interaction. So that also causes about 3.8 as well. So they cause about 11.4. Yeah, 11.4 amount of the interference, the discomfort that only can be overcome by this much energy will generate here. So there will be 2, 1, 3, 1, 3 diaxial interaction there, and also on the top of that, because of these 2 metal group on the Gauss formation here, conformation, they also, even though it's a stagger, there shouldn't be no strain over there, but they will experience a little bit of a discomfort there too as well, because they're big. This is what's happening over here. So in total, it's about 11.4 kilojoule per mole. Kind of makes sense, is it? Is it good? Okay, fine. Okay. All right, so if that is the case, let's look at this one too before we do the wing flip. Now you have this one. We'll also do, right? You see also there'll be 2, 1, 3, diaxial. What's the sound? You stop the traction, right? You see that, right? There are 2 traction there. And also, if you look at now we're looking at this way. So we're gonna put this one as a front carbon. This was on the back on this direction. So if that is the case, there'll be 2, 1, 3 over here. And we'll put this one on this side. So if you look at this one as a front carbon, this is on the back. Okay. This is on up position, right? You see? It's up. Okay. And this one now it's on this side. Okay. Here. Okay. So this also show you what? 60 degree away from these 2 method group. Also show you Gauss the conformation, that also shows about 8.3 as well here. So in total, in here, it also shows about 11.4 kilojoule amount of discomfort. This will create on cis 1,2 dimethyl cyclohexane. So the bottom line here is when you do the ring flip for just the 1-methyl and not one, but the 1-methyl attached to the cyclohexane, the one that has equatorial position is more preferred, right? Because of they can avoid all the discomfort. But if it's in cis form, either way it's still same, right? They're going to show the same amount of the discomfort anyway, so there's no preference here. They can go either this form and this ring flip, 50-50%, just no preferred form here for cis. Okay. Because of the same amount of the discomfort they express anyway in either side. Okay, so the kind of makes sense, right? We okay, good. Can I move on?
Yeah.
Oh, good. So I'll keep telling you that this cis form has no preference right here because the trans will have one. So here it's coming. So the trans is so let's start the trans. The trans means same here, but just different way. So we put it in the same side, cis, but we're gonna put those 2 methyl group on the other side. So it looks like this. So one heading front, the one heading backward over here. So they're totally on the different side of the position based on the plane on the cyclohexane here. So obviously it's just also implied hydrogen there. This looks like this. Okay. So this is what it looks like. So let's try to do the ring conformation again. Okay. Try to do here. So if you do this one here, maybe I can do the same. So maybe I'm gonna put these 2 on these 2. Okay. Well, these are 2 over here. Same. Okay. Let's make it same to make it easier to compare. Okay. So this is up here, right? This is up, but this is on the down position. It doesn't matter. If you flip it, it could be down and up, but it doesn't really matter. So you can choose, this will be up, down, that's okay. Because as long as it's on different side, no matter what, you call this one up or down, flip it, it's the same anyway. So let's try to put this in the up, then you have to put this on the down position, right? Because it's in the now different sides, because transform. So I'm gonna put this one over here. I'm gonna put this one over here. But this is on the up, we decide. So let's try to put up equatorial position. Okay. But this one has to be on the down. So it'll be down equatorial position here. Okay, this is what we're gonna do. And then let's do the ring flip again. Okay, let's try to ring flip. So now you're gonna ring flip by just making this way, right? So go this way. So it'll be going this way. Okay? So meaning this position is right there. This position is right here. This one is here. This one is here. So you're the ring flip. Okay? So you see this is equatorial down, right? So if this is equatorial down, it has to be axial down on the ring flip, as we saw before in the previous example here. And this is the equatorial up. So if you go on to this position here, it has to be axial up now. Okay, axial up. So if you try to compare this one again, you can also do axial position of hydrogen over here. Let's try to look at this one first now. Okay. So because of those 2 axial position hydrogen up, and up, they're going to have 2, 1, 3 diaxial interactions here. And then the funny thing is, on the other side, they also have other two, in 1, 3 diaxial interaction. Okay. So in total, each 1, 3 diaxial interaction is about 3.8. But you have a 2 on the top, the 2 other 2 at the bottom, so you have 4. So that is about, I think, 15.6. Okay. Oh, sorry. It'll be from 2. So then this is going to be the lot of discomfort they experience on both sides because of the diaxial interaction there. Because they're all either up and down axial position of the two method groups. But it actually shows the opposite side, right? It says up and down, so this obviously trends. So that's a lot of energy they need to have to overcome this discomfort. But here, they don't have any axial position because it's equatorial up, equatorial down. There's no axial position. So there will be no 1, 3 diaxial interaction, but just one thing once again. Okay. There will be also only one Gauss conformation discomfort, which is only 3.8. So you look at this one here, right? This is okay, so 60 degrees away. So only one Gauss conformation discomfort there, which is only 3.8. But here it's 15.2. So obviously, unlike cis 1,2 dimethylcyclohexane, for trans 1,2 dimethylcyclohexane, they will have this form obviously preferred than this one. Because of if they want to keep this form, they need to overcome a lot of energy to make this form. So unlike the cis, the trans 1,2 dimethylcyclohexane will have this form as a more preferred form than the other. I'm sorry. Oh, my voice. Okay, so makes sense? Oh, perfect. That's very nice. Okay, so once you get to know how to draw the chair conformation structure, it all makes sense even better, more. But this is something I want you to remember. This one. Okay. All right. So today I only have one more thing I want to discuss today. That is the polycyclic molecule. Okay, compound as molecule. So the polycyclic molecule simply means you have more than one ring structure. So the very common organic compound we taught in organic chemistry, is the decalin. So decalin simply is we talk about the cyclohexane form over here, and you just try to put it on together. So you're gonna have this form here, and then you can draw actually two forms there. Oh, good. So you can draw the two form. That is, you have the hydrogen on the same side on the bridge on these two, and the other one is on the other side. This is become really important for those the hydrogen position on the decalin here is because of this structure. Is it by any chance you're majoring bio major? No? No, okay. So if you do, maybe somebody watching on the YouTube channel video, if you're doing a bio major, and also chemistry-wise, it's very important too that the most important thing about the compounds, it is mainly based on the functional groups, and also another really good important factor of the compound is the structure. So even though they look almost a similar functional groups, similar like a structure, similar like numbers of elements, but they're structurally different. It shows very different functions in the body or in the nature and all the natural phenomena. So this is why we care about this one so much. This will actually, I can actually show you. So if you do this one first, okay, you have this one, okay, and you can try to draw this one, okay. So if you look at this one here, those all carbons are linked. So there's only position they're heading up axial, down axial, right? So in this case, you're going to have a two chair conformation cyclohexane kind of like a link in the one bridge very nicely, and there's two hydrogen on the opposite side. So that is this one, okay? Because that you see the one goes up, the other goes down, right? For sure. So that gives very nice, more like in just more like in the very same plane like structure over there. But if you have the other one that looks totally different, look at this. So this is when obviously this goes up here, and this one is also the same side. So because it's the equatorial down, up, down, up. So they're technically not heading the same direction, but on the same. From here, they're heading up, up. So that makes this position over here. But if you compare these two, obviously, even though they're in almost same, like similar, like a shape, if you look at it on 2D, in 3D, it's completely different structurally. That is why when you look at the decline, try to find out the position of the hydrogen on those bridge part of this polycyclic compound is very important. So because of this one, that gives us the very different structure over there. Okay, so there's a. So it's actually kind of fun if you do it this way. You can make it more like differentiate, which is this is really famous basic. This will not be on the exam, so don't worry about this one. I'm just saying this form you'll see so many times because it's a very basic type of a lot of things, cholesterol, hormones, and everything. And in this case, you can draw this one, and this one, and so on. So this is what actually we just see in the like a real reality. For our convenience, we just print this one. Just it's I don't know. That's easier to just draw. But actually, what it looks like is this. But this won't be on the exam. But the decline one, please remember, if there is a trans or cis, they will show you very different in structure because of the position of the hydrogen bridge. Okay. Makes sense, right? Okay, perfect. Oh, so I'll just stop here today. Okay, just.